Hello, everyone. It's Mr. Bronze coming at you once again on Tuesday, January 5th. Hope everyone is doing well, staying safe, and staying healthy, and getting back into the swing of things here on our second day back from the holiday and New Year's break. All right. Before we get into today's lesson, looking back into the classroom today, and noticing that many of you have fallen behind with your assignments dating back to, I don't know, a week or so before the holiday break. I think maybe you started your break a little bit earlier than the rest of us. As a reminder, get them done sooner rather than later. Don't wait till the last week of the marking period to start trying to cram all those assignments in. Okay, so please get those back to me. If you are not sure if you've submitted something for any reason, look back in your drives. And if you still have questions as to maybe something that you see on the parent portal for eSchool with your grades, any of that, reach out to me, let me know. Again, sooner rather than later. Anything that could be a mistake, and it's certainly possible, I will fix right away, get it done. It's easier to fix it now than it is to fix it later. Okay, so yesterday had a video conversation about the counting principle. And what I would like to do to start off today is have you do a little warm up. Okay, and what I would like is the sub that is in the room for me today. Thank you for being there, first of all. And second, if you wouldn't mind in a moment, just pausing this video for about 5 minutes. I want to let the class take 5 minutes to answer this warm-up question. And then after 5 minutes, you can put me back on and we'll go through the solutions. So you can pause it now. Okay, we're back. Hopefully you were able to make your way through the 4 parts to our question. Let's take a look at what we have. 2 standard dice are rolled, each numbered 1 through 6, or each side, it should say, numbered 1 through 6. What is the probability of getting a sum of 2, a sum of 7, a sum of 5 or less, a pair of even numbers? Okay. So one of the first things that I think, if we're going to take a nice organized approach to this, is ask ourselves, what is the total number of outcomes if we're rolling 2 dice? So we'll go over here. So let's imagine that we're rolling them one at a time. So we roll the first die, we have 6 possible outcomes. And when we roll the second die, we have 6 possible outcomes again. Well, the counting principle tells us that being that these are independent events, we can go ahead and multiply the number of outcomes of each to find that there are 36 possible combinations when you roll a pair of dice. Okay, so if we talk about probability is going to be out of 36. So a sum of 2. And let's also get in the habit of writing a nice probability notation. So capital P, and in parentheses, sum of 2. Let's think about this. That means we would be adding together the numbers that we see on the dice. How many different ways can we arrive at a sum of 2? Well, the answer is 1. The only way we could possibly get the dice to add up to 2 is if we have 1 on each of the dice. So that means we have a probability of 1 out of 36 that we will roll 2 ones and therefore have a probability, and therefore have a sum of 2. And there we are. Good. All right, how about a sum of 7? So let's see, probability, sum of 7. And again, this is going to be out of 36. So when you're thinking about this, you may want to start to ask yourself, well, how can I arrive at the sum of 7? Let's start to maybe make a little list. So let's go over here. And let's say if I want to add to 7, I could have a 1 and a 6. Now, remember, we've got 2 dice, so we need to be certain that we're considering the switch, meaning if we get 1 on the first die and 6 on the second, it would be different if we got 6 on the first die and 1 on the second. Now, the reason why we didn't have to consider that in part A is because we had the same number on each one. So by changing them around, that doesn't change anything, right? All right, so let's keep going. So we could do 2 and a 5. We could also do a 3 and a 4. What else could we do? How about a 4 and a 3? Now we see this reversal of the order. 5 and a 2. 6 and a 1. So if we look here at all the possible combinations, 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. 1, 2, 3, 4, 5. There is 6 of them all together. So our probability is 6 out of 36. And if we were expressing this in simplest form, that would equal 1/6. And if you didn't already know, 7 is the most common total of numbers when you add them together on a pair of fair dice. Okay. How about the sum of 5 or less? All right, so let's think about what we can do here. I'm going to clean this up a little bit here. Let's cut this. And let's cut this. All right, let's think about a sum of 5 or less. We'll start with 5. So I'm going to make a little list right here. We could do 1 and 4, and this is what you should be doing as you're thinking your way through these problems. 3 and a 2, and a 4 and a 1. These are all the ways that we can roll a pair of dice and get a sum of 5, right? Okay. How about 5 or less? Well, how about 4? We could get a 1 and a 3, a 2 and a 2, 3 and a 1. So now we see here we have 3 different possible combinations. Let's keep rolling. How about a 3? We can do a 1 and a 2, and we can do a 2 or a 1. So now we wind up with just 2 combinations. You're going to see this pattern here. And if you were to write out all the possible outcomes, all 36 possible outcomes for rolling a pair of dice, you would see the pattern that develops. This we already knew, right? We figured this one out in part A. So now we've got 4, 5, 6, 7, 8, 9, 10. So if we want a sum of 5 or less, so the probability 5 or less is equal to 10 out of 6, which we wanted to simplify, be 5 out of 18. There we go. All right, 3 down, 1 to go. What do we got left here? A pair of even numbers. Oh my goodness. So let's take a look at what we can do here. These guys. Okay, a pair of even numbers. Well, we could do a 2 and a 2. How about a 4 and a 4? A 6 and a 6. That's it, guys. That's the only way we get a pair of even numbers. So a pair meaning 2, so they both have to be even. Oh, wait a minute. They don't have to be the same number. They just have to be even. So how about this? About a 2 and a 4, and also a 2 and a 6. So a 2 and a 2, a 2 and a 4, a 2 and a 6. Okay. We could do a 4 and a 4, a 4 and a 2, 4 and a 6. And we've got a 6 and a 6 first. We've got a 6 and a 2, and a 6 and a 4. Because 2, 4, and 6 are our only even numbers that we see on the die, on each die, excuse me. And we had to make sure that both dice, when rolled, showed even numbers. So it looks to me like we've got 9. All right, so let's go ahead and put our answer together. So the probability of a pair of evens is equal to 9 out of 36, which actually reduces down to 1 out of 4. And there we are. All right, so hopefully that got you guys thinking a little bit. Either woke you up during third period or kept you from falling asleep in eighth. We'll see. All right, enough of the bad teacher jokes. Let's take this conversation forward. We're going to revisit permutations now. I know the week before break, that full week when I was first out, did a couple lessons with permutations. But as we know, when we have vacations, knowledge seems to disappear. So we're going to bring that back. So we have take 2 on the permutations. So once again, refreshing your memory banks. A permutation is an arrangement of objects in some specific order. Okay, and that is the key here. So if you are a person who likes to highlight their notes, I would highlight specific order. That's the key, because we're going to talk about soon enough combinations, which are also arrangements of objects, but here the order in combinations isn't important. In permutations, we know the order is important. All right, now we have 2 possibilities with permutations. In some of the cases, we use all the objects available to make different arrangements. For example, let's say at home you have a shelf in your room for your textbooks for school. Let's say you have 5 different textbooks. We might ask, how many ways can you arrange all 5 of your textbooks on that shelf? So that way, in this case, you're using all the objects available. You have 5 textbooks, you're arranging all of them. Well, there's also other cases when we use fewer than all the objects available. So a question might say, you have 5 textbooks. How many different ways can you arrange 3 of the 5 textbooks? Okay. So these are the 2, if we want to kind of break it out into 2 major types of questions, there you have it. So let's do example number 1. We've got my buddy, Mr. Netwich. So in Mr. Netwich's class, there are 4 students in the first row. They are Jane, Eve, Troy, and Nicole. In how many ways can Mr. Netwich call on these 4 students to present one each of 4 problems at the smartboard? So let's say that you came into Mr. Netwich's class and he gave you a 4-part warm-up question. And then he selected these 4 individuals and he wants them to present their answers up on the smartboard. Smartboard, excuse me. How many different ways can he call on them? Well, what we could do, and what we saw yesterday in the counting principle lesson, was we could actually write out all the possibilities. And I believe we did that with 3 items. And it was a pretty good size list. Go out to 4 items, that list starts to get a little burdensome. So let's hold off on that. I just kind of introduced it and said, hey, remember we could make that list? We could take the first letter of each student's name, and then I could start making the arrangements. So here's Jane, Eve, Troy, Nicole, or Jane, Eve, Nicole, and Troy, or Jane, Nicole, Eve, and Troy, and many more. I didn't want to bore everyone to death and say, let's make this whole big list, because it's not worth it. Okay? There is a better way. And the better way involves using the counting principle. And you might be thinking, well, how does the counting principle now become involved with permutations? Well, order is important, right? It's a permutation. Counting principle tells us that if you have events that are happening in order and one event doesn't affect the other, we can multiply all the possible outcomes together and get all the possible arrangements or combinations. So let's take a look at how this is all going to play out as we combine these 2 ideas together. So let's think about how Mr. Netwich could select the students to present the problems on the smartboard. So he's got 4 problems, right? 1, 2, 3, and 4. So he hasn't chosen anyone yet. And he looks at these 4 people in his first row, he initially has a choice of 4 different students. Okay, makes sense. So then he chooses one. They go up to the board, they put their solution, they sit down. So now we're on to problem number 2. Now he has a choice of 3 students. One student's already presented their answer, they're done. So now he chooses one of those 3 to put the second problem on the board. And then that's done. Then we're on to the third problem. Now there's 2 students left. He has a choice of one of the 2 students there. And finally, when that student puts the third problem on the board, there is 1 student remaining. So with each student that he selects, he reduces the number of students available for the next problem by 1. That makes sense. So what does the counting principle tell us? Counting principle tells us that we are performing these events in order, or Mr. Netwich is, and we can multiply the possible outcomes together. And what we find is he has 24 possible ways in which he can call on these 4 students to come up to the board and present an answer to one of the 4 questions. And this is really, I really like this illustration because it really kind of breaks down and shows us one by one with the problem, how these numbers, the 4, 3, 2, 1, where they come from when we multiply them together. We use the counting principle. All right, so with that said, kind of lays the groundwork for what we're going to do with permutations, what we're going to continue to do. So let's talk about notation. So for this example that we just did, we showed that the math behind our answer was 4 times 3 times 2 times 1. Well, that exact expression can be written using notation. Okay, what we can do is we can use this notation right here for permutations. Notice we've got a P in the middle, a 4 on the left, and a 4 on the right. We're going to talk about what those 4s represent. Not only the 4s on the left and the right, but they are what we call subscripts. They're the opposite of superscripts, which are often what we see as exponents. So they're dropped down low, and they're made a little bit smaller. Now, if you were going to read this out loud, you would say, this represents the number of permutations of 4 things taken 4 at a time, right? Because we had 4 students, and Mr. Netwich selected all 4 of them to go up to the board 1 at a time. This expression, 4 times 3 times 2 times 1, is also equal to this notation, 4 with an exclamation point after it, which we know and love is our factorial. So you can read this as either 4 factorial or factorial 4. And generally, we see it written, and we hear people read it aloud as 4 factorial. All right, so we're kind of starting to connect the dots here. We're bringing in our notation. We've connected the counting principle to permutations. So here's kind of a summary of these 2 bullet points up here. What we're saying is the number of permutations of 4 things taken 4 at a time is equal to 4 factorial, which is equal to 4 times 3 times 2 times 1, which is 24. So all of these expressions and values are all equal. They represent the same quantity, the same amount. So we have a general rule, of course, and I gave this to you right in your notes. Some people are formula people. They love formulas. They want to see the formula. Where did this come from? Give me a formula. Well, here you go. So in general, when we're talking about permutations, and you have n things, n represents some number, right? Before we mentioned, say, 5 textbooks, and we're going to take all 5 of them and arrange them on the shelf. We could figure out the number of arrangements by evaluating 5p5, which would be equal to 5 factorial, which if we wrote it out would be 5 times 4 times 3 times 2 times 1. Okay, always counting down to 1 integer at a time. All right. And a lot of this, goes back to the first time around when you saw permutations and combinations, which I believe was back in your middle school days. And with the changing curriculums over the years, who knows if you have seen it since then, but we're bringing it back. All right, let's take a look at another example together. Got my buddy, Mrs. Angelo. So she has a class of 25 students, and she assigns 3 problems for homework. And how many ways can Mrs. Angelo call on any 3 of the 25 students in her class to present 1 problem each at the smartboard? All right, so let's think about how does this question differ from the prior example. In the prior example, Mr. Netwich decided that he was going to select 4 specific students to put the 4 questions on the board. So he kind of narrowed the scope down. So out of the students available, he decided I only have these 4 students available. He's going to select all 4 of them. Mrs. Angelo is a different approach. She is going to break this wide open. She said, I'm not restricting it to just 4 students. I've got 25 students in this class. Everybody in this room is fair game. So how many different ways can she select any 3 of the students out of the 25 in there? So now we're not selecting the entire total. We're only selecting 3 out of the total of 25. All right, so that is the big difference. So of course, what we see here, order certainly is important, right? Because if we have Joe, Sam, and Mary, having Joe do number 1, Sam number 2, and Mary number 3 is different from having Mary do number 1, Joe number 2, and Sam number 3. So order is certainly important here. And we're going to use permutations of 25 things. That's our total, taken 3 at a time. All right. So again, I'm pointing out here that not all 25 are selected, so not every object is being used. So let's think about this. Let's work this out since this is a little bit different. So we've got problem number 1, problem number 2, and problem number 3. And Mrs. Angelo is going to pick. So she starts with problem number 1. Now this, we already agreed, was a permutation of 25 things taken 3 at a time. And remember what that looks like. When Mrs. Angelo first goes to select a student for problem number 1, she has 25 students to choose from. So that she picks 1. So now for problem number 2, she only has 24 to choose from. And then when she picks another student, now she only has 23 to choose from. And that's all she needs because she only is selecting 3 students. So that said, 25 choices times 24 times 23, she has 13,800 different permutations or different arrangements of 3 students that she can select from the 25 in the room. Crazy, crazy, crazy. All right, with that said, for you formula people, here it is. So here's our adjustment. So this is when we are selecting the number of objects less than the total that we have. So what we wind up with here is now the number on the left of P and the number on the right of P are different. The number on the right will always be less than or equal to. Okay, and again, we will count down. Now the difference here is we're not going to continue until we get down to 1. Whatever this number is, that's how many factors we're going to multiply together. So let's go back up here to what we did. Take a look, 25p3. The 25 on the left tells you the number to start with. The 3 says we're only going to multiply 3 factors together. So when I start counting down, I'm going to stop when I have 3 different factors here. Then I'll take my multiplication. Find myself a nice product. All right. Hopefully everyone is able to key in on this without much of an issue. Let's move forward. Practice number 1. Evaluate 10p4. We're going to start with a practice problem that goes back to the real basics. There's no story here. There's no song and dance. Just giving you a permutation. Say, hey, what is the value of this 10p4? Now, we know we're going to use multiplication, counting principle, right? We also now know that when we have our two values of n and r, just remember, get my pen out here. On the left is n, lowercase n. Then we have our p, and then on the right, lowercase r. When n and r are not equal, n is the number we start with. So we're going to have 10 times 9 times 8. And we're going to stop writing the numbers when we have 4 of them. And here we are. So if we were to write it out by hands, 10p4, we're going to multiply together 10 times 9 times 8 times 7. 5,040. Easy enough. But we want something even easier, right? We always want something a little bit easier. How can we use technology? Well, if you have your calculators, take them out. Yes, we have permutations in the calculator. So I have given you some screenshots for my calculator showing you what we need to do. Here we are. Okay. So our problem was 10p4. Now, here's the thing we want to remember. Whatever number comes on the left of p, you have to type that in the calculator before you do anything. First, you put in your 10. Then you press your math button, and here's your menu. Then you use your right arrow to go from your math submenu, you scoot across the top to the probability submenu, PRB. Once you're there, you select option 2, which is NPR. When you do, NPR pops up. And then you type in the second number, which for us was 4. And then you press enter. For some of you who have a newer operating system, when you do this and you get to this screen here, there'll be no N or R. The 10 will actually be here in the N place, will be in the subscript, and the 4 will go in the subscript here. Okay, that's the only difference between the new and the old operating systems. You still go through the same menus, the same steps. It's just that this screen looks a little different. Then you press enter and you get your answer. And you're good to go. So that's kind of nice. All right, how about another practice problem? So we're going to talk about making different words. Now, when we talk about making words, we're not talking about the Queen's English. We're not talking about being able to look the word up in a dictionary. All we're saying is it could be a ridiculous word that makes no sense. We're just rearranging the letters. Okay. So here in part A, we're going to take the word angle. 5 letters. They're all different. Okay. And we're going to figure out, if we use each letter only once, how many different 5-letter words we can make. So, first off, we've got a permutation, right? Order's important. If we use the same 5 letters, if we start changing the order, it's a different word. So that means order is important. We've got 5 letters in total, and we're going to use all 5 of them because we're making a 5-letter word. So by thinking our way through this, say, wait a minute. We can do this one of 2 ways. We can first say, you know what? I've got a permutation. I'm using 5 letters. There's my text options that I love. All right. Little subscripts. I've got a total of 5 letters. I'm going to use all 5 of them. And what have we learned today? Well, we learned that's equal to 5 factorial, which also means as long as those 5s are the same, right? Those numbers are the same. That's 5 times 4 times 3 times 2 times 1. And yes, you can put that right in your calculator if you want. Put 120. There you go. So hopefully, if you have your calculators, we're not having much in the way of difficulty. If for any reason you have any calculator issues, please email me. I can probably help you with them right away. Excuse me. How about a follow-up question? Change the tune just a bit. We're going to use all 5 letters from the word angle, but now we want to determine how many 3-letter words can be formed. Okay. 5 to choose from. We're only choosing 3. So now our permutation changes. We still begin with the total number of letters that we have, but now we're only selecting 3 of them. All right, so let me put this in the proper notation real quick. We do want to be technically correct. All right, now this is not equal to a factorial. Up here, the factorial only comes in, we only use factorial if these 2 numbers are the same. These 2 are not the same. So remember, the first number tells us the number to start with. So we're going to begin with 5 times. And then we go down to the next integer, which is 4 times. And we go to the next. And we stop there. And the reason why we stop is because our second number told us we only want 3 factors here. 1, 2, 3. So we take the product of these 3, and now we find there are 60 different 3-letter words we can form. Okay, I really like this opening question. It really kind of shows the difference between the 2 based on what we know about permutations and their connections with factorial, as well as the counting principle. So we're kind of putting a lot of things together here, which is kind of nice. All right, hopefully everyone is on board. All right, let's get on to the next one. Now, 3, we're going to mix it up a little bit. A 3-digit numeral is formed by selecting from the digits 4, 5, 6, 7, 8, and 9 with no repetition. So you can only use numbers once. How many of these 3-digit numerals will be greater than 800? All right. Now, Mr. Bronze has made things interesting. So hopefully Jack Grossman is not sleeping. You sleeping, Jack? All right, we'll see. All right, so I'm going to map this out. And I love using mapping strategies. Here's my 3-digit number. We introduced something new in this question. I'm going to highlight it right now. You know what this is right here? This is what we refer to as a constraint. CONS. I'm trying really hard to write neat. I hope you guys know I'm using a mouse right now. It is not easy. This is a constraint. What does a constraint do? It limits the amount of options you have. It didn't just say, how many 3-digit numerals can we make? We don't care what it looks like. It's now saying it's got to be greater than 800. So think about that. If this number that we put together has to be greater than 800, we have to worry about the hundreds place. This is where the constraint comes in. We can't put the number 4 here, right? Because that would be a number in the 400s, or 5, or 6, or 7. Those would be 400s, 500s, 600s, and 700s. They're all less than 800. How many options do I have out of these numbers really to put in this place? I only have 2. I can only put in there the 8 or the 9. Now, if I put either the 8 or the 9 in the hundreds place, does that guarantee me a number greater than 800 based on the rest of the numbers that we have up here? The answer is yes. And that's good news, because that means it doesn't matter which numbers we put here and here. Now, what I want you guys to remember is these numbers that we fill in, we're talking about how many options we have. How many different numbers can I put here? I can put 2. Now, I'm only going to put 1. I'm only either going to put the 8 or the 9. So since we had 1, 2, 3, 4, 5, 6 digits to begin with, and we're not allowed to repeat. If I put 1 digit here, now I can put any of the remaining 5 digits here. And once I put a second digit here, I can put any of the remaining 4 digits here. This is the This is the trickiest type of arrangement question when you have constraints. As far as calculating, we are still going to use multiplication. And we wind up here with an answer of 40. So when you have a constraint, you always want to make the constraint the first digit that you deal with. Okay, it won't always be in the hundreds. Maybe it's in the tens. Maybe it's in the ones. Maybe it's in the hundreds of thousands. We don't know. Depends on the question. All right, and I think that was the last question for today. It is. All right, so I have attached a homework assignment for you in the stream. So if there is time left in the period, please get started on that. That will be due by midnight tonight. So anything that you don't finish during the period, please finish at some point today. And again, if you are behind in homeworks or any other types of assignments, get those to me as soon as you can, please. All right, it's been another fun day together. Everyone stay safe, stay healthy, and I will see you soon. Have a great day, guys. Bye-bye.